All right, we've got our work cut out for us here. We're told the KSP for calcium hydroxide is 6.5 times 10 to the minus 6th. We take this solid, we place it in water, deionized water, dissolve it to reach an equilibrium. We want to know what is the expected calcium ion concentration once that equilibrium is reached. We also want to know what's the molar solubility and what is the expected pH of the solution. We start at the usual place by writing the correct formula for the sparingly soluble salt. Because calcium is a group 2 metal ion and hydroxide only has a -1 charge, we gotta need 2 copies of hydroxide for every 1 calcium. So when we write the equation for the dissolution, we make 2 aqueous ions of hydroxide and only 1 of calcium. That'll become important in a little bit to keep track of that. Now we proceed by their usual route. When we're working equilibrium problems, we become accustomed to using this Rice table approach. Fortunately, when we're dealing with dissolving solids, that material on the left's always a solid. We don't even need to keep track of it because it doesn't appear in our equilibrium constant expression. As long as some of it's there, we can establish an equilibrium, and if some remains present inside the beaker, we're good to go. Now, but because this was deionized water, before any of this dissolves, our concentration of both of these ions are essentially 0. Hydroxide I might put approximately 0, because we know in aqueous solutions like water-based solutions, there's always a small standing concentration of hydroxide ion. But for our purposes here, we're going to say that that's 0. We're going to ignore that contribution from the dissociation of water, or autoionization of water. We're going to make some calcium. We'll make twice as much hydroxide by virtue of the stoichiometry. And we'll have X concentration and 2X once our equilibrium is reached. Since we've now learned how to write the KSP expressions as being equal to the equilibrium concentrations of the ions multiplied times one another, that one we have to square because of that 2, we can then substitute into that expression what our expected values are. X for our calcium concentration, and 2X is our expected concentration at equilibrium for hydroxide. Now we solve for X just like we would in any other equilibrium problem that we've worked. We know that the KSP is 6.5 times 10 to the minus 6. So you substitute that in, set it equal to X times 2X squared, and you basically solve, okay? So the first thing I do is square this 2x, which makes 4x squared. And then once you multiply it by the x again, you get 4x to the third power. And that equals your KSP, 6.5 times 10 to the minus 6 in this case. So if I want to solve for x, it looks like x is going to be equal to the cube root of my KSP, 6.5 times 10 to the minus 6 divided by 4. All right, so you take the KSP, divide it by 4, take the cube root, not the square root, but the cube root, right? So make sure to do that on your calculator. Something to pay attention to in the mathematics. So if we go and we crunch some numbers, see what we get here. 1.2 times 10 to the minus 2. I believe that's what I got here. 1.2 times 10 to the minus 2 for my x. All right, so now I'm going to erase some of this work just so I can make sense of all. Oops, not the right tool. Okay, erase some of this work so I can make sense of all this. So we solve for x. Now let's give it chemical meaning. We now know what the concentration of calcium ion is expected to be once an equilibrium is reached. That molar. I also know, since my hydroxide's twice as much, or twice as much as produced, I should get 2.4 times 10 to the minus 2 molar of hydroxide ion present in my solution. So because I was able to solve for x relatively straightforwardly, down here at the bottom that I'm erasing right now, I now know the concentration of my ions. So let's go back and see if we can start answering these questions that we were posed. We wanted to know, what is the calcium ion concentration? That's pretty easy now. That's just equal to x, isn't it? 1.2 times 10 to the minus 2 mole per liter. We're also asked, what is the molar solubility of the compound, the calcium hydroxide? Well, since it's a 1-to-1 ratio, the molar solubility is the same as x, because that's how much of that stuff we can get to dissolve. 1.2 times 10 to the minus 2 moles per liter. Easy enough. Now the last problem, kind of interesting. It asks us about the pH, right? Any insights on what might can help us figure that out or help control the pH here? Didn't we mix some hydroxide? In fact, we know the concentration of that hydroxide is 2.4 times 10 to the minus 2. So if I took the negative log of 2x, which is 2.4 times 10 to the minus 2, wouldn't that be a great estimate of my pOH? Because remember, pOH is nothing more than negative log of the hydroxide ion concentration. So I'm going to do that on my calculator. Negative log of 0.024. When I did that, I got 1.62. Now that's not my pH, that's my pOH. Remember, my pH is going to be equal to 14 minus my pOH, or 1.62. So this solution is going to be pretty basic. That's all is said and done, isn't it? But I can figure it out. I just need to do 14 minus 1.62, and I get 12.38 as my answer. And that's my pH, all right? So because I understand the solubility equilibrium, I can do all these things. I can figure out the concentration of one of my ions. I can figure out the concentration of the second ion. I can figure out the molar solubility. And since in this case, we make the hydroxide anion, I can figure out what the pOH and the pH is. All right, so it's an interesting problem.